This talk is basically split into two parts. First of them is without GANs. So all of you that are here just for GANs, you can leave. Maciej is going to take the most complex one with GANs. I'm going to take the one without GANs, but I hope you're going to enjoy the ride. So representation learning. Obviously, as every single good machine learning talk, we need to start with a cat. So here we go. If you want to search for similar images, or if you want to search in general for things that are similar in some space, one of the most important things that you need to figure out about your data is how to represent it. That's either through some complex machine learning algorithms, or just by looking at pixel values, or just by looking at characters in your words. Whatever you do, at the end of the day, it's a representation that you built of your data. So in the case of images, what you could easily do is you can take a pixel of an image and compare it with the rest. And then square it just to make sure that the distance between those two representations, very naive ones, are symmetrical. So let's say that you have a cat and a database of images on the right. There is a koala, a zebra, a bunch of other animals. And you just take pixel by pixel differences. You square them up, and you get some sort of a distance between them. Now you can do the same sort of a trick with zebra. And just a hint here, zebra looks pretty similar to this particular cat due to the lines and stripes. You can also do the same thing with another cat. There's a bunch of other animals that you can compare your image to, just pixel by pixel. And then when you visually search those images using this simple representation, what you would get is some kind of epic failure. I mean, this is zebra. Obviously, it's not the same thing that you wanted to look for in the first place. We don't have any semantic information embedded within the pixel values themselves. We just compare them through RGBD values. So you are expected to fail, basically. If you look at the next images, then at the third place, you would get a cat. Then at the fifth, actually, a lion. So this is something that, tells you that the representation that we picked is not the right one. And this talk is basically focused on how to pick the right representation for your data. So basically, how to map your input data, images, words, videos, whatever, to a latent space of some kind. In this case, we will use Z as this is a spoiler for the GAN part. In GANs, you can use latent space as representations. You can use also some other parts of GAN architecture to represent your images. But the main point is how do you map your input data into your representation. And now we try to learn that in several different ways. First, using the simple linear methods, then through boosting, then through GANs, and extrapolate that to the other methods. So what other applications representation learning is useful for? Stylistically similar visual search, and that's part of the work that you might have seen before. It's style search developed at Tooploox, where we basically look for similar images both in terms of style, so similar objects both in terms of style and the visual similarity. This is a mobile app that you can test through website as well. Another application where representation is needed is SLAM, so simultaneous localization and mapping. And that's an algorithm that is a core part of many augmented reality apps. In this case, we're looking at Hansel. That's another product within Tooploox that we developed that allows you to move from one place of a building to the other using some breadcrumbs that you see in the right corner of this screen. So basically, and the third one, natural language processing tasks such as classification, keywords extraction, and so on, where you need to find a representation of your data between words, characters, and some vectors. This is the talk of today. We start with first two methods that are not neural network based, so that you still get a feeling that there was something before neural networks out there. Then we will move to Siamese descriptor, so Siamese representation learned with Siamese architecture. That was published this year at the ECCV workshop. And then we will move on to the work that was mentioned before, the one about GANs, and look out for the next ones. So let's start with the first part, the efficient discriminative projections for binary descriptors. That was work published at ECCV in 2012. So moving from the representation itself, you can actually make it more compact and more memory consistent or memory efficient using binarization. So that basically allows you to put some additional constraints or representation, not only just use a floating point vectors, but binarize them to make them more compact and also more memory friendly. This is important for many tasks again. In this particular case, image retrieval is something that we were looking at, but also image matching and hashing images, so taking an image and putting it and hashing it into like a single hash of your data. That's where binary descriptors are especially important, because once you have a hash, you don't really need to go through this traditional methods of searching using Euclidean distance. You just do Hamming distance or even constant complexity search within your hash map. So that makes your representation of your data super efficient. Okay, so how does the binary descriptor look for an image? How does it look in practice? One way is basically taking your image, your input image patch X, projected with a bunch of projections, W, and at threshold and binarize that. Now, when you want to train those projections somehow, you can use many different objectives. One of them, if you're working with pairs of images, is to make the pair of images that describe the same 3D point or the same point in space to be as close to each other as possible. And the other images, or the images that describe different 3D key points, push far away in the binary space. This sort of concept will be also used in several other papers that we talk about in this talk. So I hope it's gonna stick. Once you look at those projections, the main problem when you're projecting your image patch is that they are fairly complex to compute. So once again, you would need to go through pixel by pixel, and every single projection would need to be multiplied one by one. That's pretty complex and takes a lot of time. So what we come up with is a method to basically simplify this operation through a set of dictionary elements. So you basically take the projection and you approximate it with a bunch of fairly fast to compute elements of a dictionary. This changes the objective function that you want to minimize. And on top of the approximation, you also add a sparsification constant. So sparsification part of the objection function basically makes the number of elements of your dictionary that you use to approximate your projection as small as possible. This is the L1 norm put on the number of projections. So sample approximations that you get this way look more or less like that. These are the projections that you learn from your data. This is the left side of the first images in the left side of the image. And then once you go towards the right, you see how more and more constrained we are with the approximation, and how less and less the approximations actually look similar to the original projections. But we get what we were actually asked to do. We get the projection, and we get the approximation of the projection, which is much faster to be computed, because you just pick several elements from your dictionary and you compute them at a given point of the image. Similar for the Gaussians. And this is how we compute our first descriptor, the debrief. That was, back in 2012, published at ECCV. However, we were not able to outperform the state of the art at that point. The main reason why that was the case is, as you see the linear combination of those elements, it's fairly simple. It doesn't really provide any additional non-linearities that are so well known from neural networks to be working fairly well. We were much better than the state of the art in terms of binary intensity-based descriptors at that part, but not necessarily beating the state of the art in general. So we looked at something that is a little bit more complex, which is boosting. And we came up with an idea of using boosting for learning the descriptors as well. The paper was published in 2013 at CVPR, and it's called Boosting Binary Key Point Descriptors. Okay. So the idea is a little bit different. instead of just mapping and trying to minimize one objective function, we're trying to learn the whole similarity between two image patches, or actually pairs of image patches. So in the case of negative labels, so in case of the images that are actually looking at different 3D points, you want to move them or map them to like a similarity measure that is negative. That means that they basically correspond to things that are very, very much different. Now, in terms of the positive labeled data or positive labeled pair of images, you want to move them to the positive part of the similarity measure. And how do you do that? You basically use boosting, which gives you this fairly interesting objective function with exponential loss. Wherever there is a mismatch between the label and the metric, so the function f of subscript c, then you get the highest, well, then you get an increase in your function, and when there's much, then they are aligned, and in this case you go down your objective function. Now the trick is, how do you actually come up with this f of subscript c? The typical way where you're using boosting is by applying several and adding several weak classifiers. In this case, we are using actually weak classifiers both on the left and right image. So on the pair of images themselves, they are one and the other one, and they're actually used where the same weak learner is used in both of them. And you multiply them by alpha. This is part of the boosting that is well extended in AdaBoost. You find the alpha parameter through optimization on your training data set. Yeah, so for those of you who haven't heard of boosting, this is a fairly simple method that basically allows you to add several weak classifiers or weak learners, combine them together, and get the strong classifier out of them. So in this case, we would basically start with simple classifiers such as intensity comparisons. Basically, you take 2 parts of the pixel or 2 parts of the image, and you compare the intensity in those 2 points. This is how you get 1 or 0. And then the gradient-based weak learners. This is a little bit more tricky. You basically sum the magnitude of gradients within a given region of image, and you compare it with the whole image patch. But still, you get a similar output, which is a binary 0-1 classification from weak learners. You combine multiple of them, and then you get a fairly strong output. The results allowed us to basically beat state of the art at that point. So we were better than SIFT, which was and still is a golden standard for descriptors and image descriptors in general. So we were at that point pretty happy. This was more or less the time when neural networks started to rule the world. That was 2013. A lot of people actually moved to looking in how to train a neural network to find the same representation of images. However, at that point, there was no clear idea on how to binarize them properly. Binarization at that point was pretty much considered to be, well, non-differentiable, and we were looking at very harsh approximations of binarization to get that thing to work. Okay, these are the results basically of still bin boost, and now this is the part that we sort of rediscovered this problem again, now from a slightly different perspective. Part of this work was actually presented last year here at PL and ML. The descriptor that we proposed is basically a combination of descriptors from a neighborhood of an image pixel. So say that you have a central point over here in the middle of the teddy bear, but you are interested in a descriptor that takes a little bit more holistically the whole image. So what you can do is, obviously, you can increase the size of the patch that you analyze, but you can also look at several other key points that were detected in the neighborhood of your central key point. And this is what exactly we did. We took the central key point as well as the descriptor for the central key point and the relation between those key points and their neighbors. We put them into a constellation embedding module, and we took exactly the same architecture on the right side. So we used basically the Siamese architecture, and then we trained a model to compute the Euclidean distance between those constellation embedding-based modules. The embedding itself basically put all the information that we have about the key points and their neighbors together. There was descriptor, there was relative pose, so relative rotation and relative orientation for the neighbors. And also they were basically concatenated in a sort of cascade way, with the output being the embedding of a concatenation of different information sources. With the results, we obtained fairly big improvement with respect to what's currently being used mostly in the SLAM application. Compared to basic ORB, SURF, and the standard, even gold standard SIFT, we observed fairly high improvement. So this is pretty much it when it comes to the without GANs part. Now Maciej is going to take the next steps, which is how to actually incorporate GANs into this whole descriptor learning part.
Hello. Hello. So I'm going to present our two recent papers related with representation learning. The first paper, we call it BIN-GAN, the model that is described in this paper, is about learning representations, binary compact representations using deep generative models. So, as Tomek mentioned before, we aim at learning compact binary descriptors, and currently everyone is using deep learning solutions, so we are also using deep learning solutions here. And the basic idea is to put the image on the input and receive the compact binary coding on the output. And it would be perfect if the similar images would have similar codes according to the Hamming distance. So the question is, how can we define the loss function that it would be beneficial in terms of learning binary codes? Tomek mentioned our Siamese networks, it was one possibility. And in our work, we are utilizing the good properties of the discriminator that are obtained during the adversarial training. So particularly, we are using GANs and the discriminator, not the generator, which is usually used to generate images as a network that is going to represent our images. So just a brief introduction to the GANs. We have workshop on Monday about GANs, but not all of you are familiar with this framework probably. So we have two fighting networks. We call them generator and discriminator. The role of the discriminator is to distinguish between fake and true images, where the fake images are generated by the generator. So generator is trying to fool the discriminator by generating better and better fake images. And the entire framework in classical way is trained by maximizing and minimizing the cross entropy loss. So for our model, we utilize the so-called feature matching technique. That is the matching the statistics of fake and true images using some feature space. In this example, we use the feature space of the discriminator to represent the data. So we are matching the statistics of the images according to the intermediate layer of the discriminator. And for the discriminator part of training, we are using the traditional cross entropy to train the discriminator. And however, it was proven before that during these loss settings, we are capable to train the good representation of our images that is stored on the last layer of the discriminator. The problem is that we are focusing on learning the compact binary descriptors. So we have to incorporate some additional regularization terms in the criterion that is used to train the discriminator. So we propose two regularization terms. The first one is called binary representation entropy. And the second one is called distance matching regularizer. So let's have a closer look to these regularization terms. So here is our structure of our discriminator network. And we can distinguish here so-called high-dimensional layer and low-dimensional layer, where the high-dimensional layer is some intermediate layer of the discriminator, that the number of the units for this layer is significantly higher than for the low-dimensional layer. And the low-dimensional layer is going further to be used as a coding space. And we, of course, make some approximation of traditional sign function that would be used for coding by using the soft sign activation function. And our BRE regularizer is composed of two terms. The first term is moving this, forcing the expected value of binary codes. Of course, we assume -1 coding to be 0. And the second term is decreasing the pairwise correlation between pairs of the units. The second regularizer is responsible for transferring the Hamming distance from high-dimensional layer to the low-dimensional layer, where in this particular case we assume that we have hard-coded binary coding from high-dimensional layer. So we, in fact, we are propagating the gradient using a low-dimensional path. Here we present some results. The results were conducted on Brown dataset, and we used it was a task related with the image matching, and as a quality criterion we used false positive rate at the 0.95 true positive rate. And so as you can see, the results are quite nice comparing to the reference method, unsupervised reference methods. So we also evaluated our method on the task, image retrieval task, and we used a CIFAR10 dataset, and we used mean average precision as a quality criterion. On the right side, you can see some test images and the top dataset images that are the closest according to the Hamming distance. And now we are going to present our recent work that is related with generating and encoding 3D point clouds. And our model is, we aim at constructing end-to-end autoencoder with the probabilistic latent space that will allow us to sample from unseen examples, interpolate between examples, reconstruct images, or we can use this representation for clustering or classification purposes. So the architecture of our autoencoder is as follows. We represent the input point clouds as list of points, and we make use of the point net as an encoder because it's a permutation invariant, so we easily can permute the list of points on the input and the output of the network remain unchanged. Moreover, we are using as a reconstruction loss earth mover distance. This is distance that represents the number of actions. We can interpret it as the number of actions that is needed to transform one point cloud to another. And to receive the probabilistic representation on the latent space, we are applying here the adversarial training. So we assume some prior distribution PZ, and we force the distribution of the latent space to be the same in adversarial training. So we are generating the samples from the prior distribution and train the discriminator, the additional neural network that can be observed here, to distinguish between fake and true examples, where the fake examples are simply generated by our encoder. So in this particular architecture, the encoder plays two roles. The first role is to encode the 3D point cloud into the latent space and and generate artificial samples similar to the samples generated from the prior distribution. So here we can see the results of this adversarial training. Here we have the simple autoencoder, and there we can observe the adversarial autoencoder. So you can see that the distribution for the adversarial autoencoder is pretty good. And for the autoencoders, for the simple autoencoder, we can observe interpolation gaps like here. Practically, it means that if we take two chairs and try to interpolate between those two chairs, we can observe some sharp jumps for the autoencoder, which is baseline here. And we have some smooth interpolation in terms of our method. So practically, it means that we receive, during the interpolation, we receive some good interpretable chairs represented by the point clouds. And here are some additional results. So here we have the generated samples from our model. We can also sample from the prior distribution and generate artificial samples. Some more interpolations. You can see that we can interpolate between those two objects, and the intermediate objects during interpolation are also real good-looking 3D point clouds. So this structure, sorry for that. So this structure of adversarial autoencoder can be also applied to the task like clustering, for instance. So we extend our model with additional discriminator and add additional coding unit to the latent space. So why is additional coding unit? Where this coding unit is one-hot coding, and the role of the additional discriminator is to train some hidden classes of the chairs. So on the right side, you can see that we can discover some clusters of the chairs with the particular features that can be observed. For example, we have some bar chairs or some fancy other chairs. And this is obtained during the adversarial training, where we sample Y from the categorical distribution, and the discriminator is trying to distinguish between the true samples from categorical distribution and the fake samples generated by the encoder. So an encoder is generating Y samples and Z samples in parallel. Okay, so that's all from my side.
Okay. So, in conclusions, to go and give you sort of like a final take-home messages from this talk, learning representation can be useful for many retrieval tasks. That's both related to visual, multimodal, textual input. We went through a bunch of binary descriptors. In this case, that's because they are fairly efficient and cheap to store, efficient to match and cheap to store. They can be learned with non-neural network-based methods, such as linear methods with approximations and boosting. We can also use Siamese nets, or, and this is, I guess, a little bit undersold by Maciej, but unsupervised methods for learning using GANs. So GANs in general are very often used in applications, and wherever you see those fancy videos online for generation of images or other data. Now in this case we actually use that for training a representation that is both compact and efficient to store. Yeah, so this is the screw up. I wanted to ask you at the end if you still want to use GANs for generating those fancy images of faces and so on, then then I invite you to Comixify, and this is actually a recent work from Warsaw University of Technology, when we were able to Comixify videos and still with GANs, but generate fancy images. So if you're into that, we can still offer you something. Okay, so last bunch of well, acknowledgements. This work is not only done by us, we have a bunch of collaborators, both in the academia and in the industry that we work with. We also like to acknowledge our scientific advisory board. That includes Krzysiek Garax from NYU, Łukasz Kiciński from Stanford, Vincent Lepetit from University of Bordeaux, and Kwong from University of Victoria, and Alex from University of Washington. And if you have any questions related to this topic or the others, we're there at the booth. We would like to also invite you to take a look at our AI residency program. That is a program that we start next year. It's mainly focused on, well, basically doing research, pure research, no commercial projects, no strings attached, just research. We're going to have a one-year residency program starting in March or April, May. Next year, there's all the details are in the QR code and on the link under the URL. And if you have any questions related to this topic or any other, we're going to be around here. So thank you again for your attention.